Portland, Oregon. 22 January 1943. Dockside thermometers registered 4 degrees Celsius. Remnants of overnight frost whitened the timbers along the Willamette River. At outfitting berth 7, stevedores loaded crated truck parts aboard the nearly completed Liberty ship SS Schenectady. 2 Coast Guard inspectors finished their routine hull survey and signed the log at 0800 hours. Commanders in Washington expected this vessel to join convoy HX-224 by mid-February, delivering 10,441 gross tons of cargo to Liverpool or Murmansk. Naval architects calculated that a well-maintained welded hull should endure at least 5 years of Atlantic service. The reports soon showed otherwise. At 10:15 hours, without warning and under zero external load, the Schenectady emitted a sound described by witnesses as a rifle shot. Within seconds, a fracture opened from deck to keel, splitting the motionless ship cleanly amidships. The age of brittle fracture had arrived.
Washington, D.C.
For February 1941, a typewritten memorandum arrived at the United States Maritime Commission bearing the seal of the White House and a production target that seemed, to most observers, impossible: 2,000 new cargo vessels by 1945. Planners reviewing existing shipyard capacity noted that traditional riveted construction required an average of 230 days per hull. U-boat sinkings in the North Atlantic were outpacing replacements by a ratio exceeding 3-to-1. Between September 1939 and December 1940, German submarines had sent more than 4 million gross register tons of Allied shipping to the bottom of the Atlantic. The deficit threatened to strangle Britain's supply lines before a single American soldier reached Europe. Prime Minister Winston Churchill would later write that the U-boat peril was the only thing that truly frightened him during the entire war. Industrialist Henry J. Kaiser, who had never built a ship before Pearl Harbor, proposed a solution drawn from dam and highway construction: modular assembly using all-welded hulls. Kaiser had orchestrated construction of Hoover Dam, Bonneville Dam, and Grand Coulee Dam using prefabrication techniques that slashed traditional schedules. He proposed applying the same principles to ship construction. Traditional riveted joints required drilling holes through steel plate, heating rivets to orange incandescence in portable forges, and driving them home with pneumatic hammers while still soft enough to deform. A single Liberty hull consumed approximately 3 million rivets and required teams of skilled riveters working in cramped holds, double bottoms, and wing tanks where ventilation was poor and noise was punishing. Each rivet had to be driven by a 3-man team: a heater, a catcher who received the glowing rivet in a bucket, and a bucker-up who backed the rivet while the driver applied the pneumatic hammer. Kaiser's engineers calculated that fusion welding could eliminate every rivet, reduce outfit weight by roughly 60 tons per vessel, and compress construction schedules to under 40 days from keel laying to launch. The technique employed electric arc welding, in which an electrode melted the base metal and deposited filler material to create a continuous joint. Welding had been used successfully in pipeline construction and pressure vessel fabrication, but never on the scale proposed for Liberty ships. The British had experimented with welded hulls before the war, but retained traditional riveted construction for most merchant vessels. Kaiser argued that the United States, with no established shipbuilding tradition to defend, could leapfrog directly to welded construction without the resistance from trade unions and conservative naval architects that constrained British yards. Maritime Commission Chairman Rear Admiral Emery S. Land reviewed the proposal during a meeting on 16 February 1941. Land, a career naval officer and naval architect, harbored reservations about welded hulls. The Navy had experienced cracking problems in welded destroyer hulls during the 1920s and had largely reverted to riveted construction for major combatants. Nevertheless, Land recognized that the production target could not be met using traditional methods. He authorized an expansion from 9 existing shipyards to more than 30 across the East Coast, Gulf Coast, and Pacific Seaboard. The Commission adopted a standard design designated EC2SC1, based on a British tramp steamer but modified for welded construction and rapid assembly. The first keel was laid at Todbath Iron Shipbuilding in Maine on 30 April 1941. Within 18 months, employment in American shipyards surpassed 600,000 workers, many of them women and minorities entering industrial work for the first time. Shipyard wages ran approximately $1.20 per hour for general laborers and $1.60 for skilled trades. The work was hard, the hours long, and the conditions often dangerous. Welders suffered flash burns to exposed skin, respiratory problems from welding fumes, and eye damage from ultraviolet radiation. Falls from staging killed or injured workers monthly. Yet the jobs provided economic opportunity on a scale unprecedented in American history, and the turnout exceeded all projections. Recruitment posters emphasized patriotic duty alongside wages, showing riveters and welders with the caption, "The ships we build today sink U-boats tomorrow." Monthly completions climbed from one vessel in early 1941 to approximately 140 ships by late 1943. Commission progress bulletins recorded more than 900 deliveries during 1942, the overwhelming majority featuring welded hulls. The fastest construction time, 4 days 15 hours from keel laying to launch for SS Robert E. Peary in November 1942, became a propaganda showcase, though such records required pre-outfitting most components and did not represent normal practice. A more realistic average completion time settled at 42 days by mid-1943, still dramatically faster than the 230 days typical of riveted construction. Weld inspection protocols relied primarily on visual examination and spot radiography covering a small minority of seams during the initial ramp-up. Quality control procedures, while adequate for detecting gross defects such as lack of fusion, incomplete penetration, and large slag inclusions, did not systematically assess low-temperature toughness or notch sensitivity in parent metal and heat-affected zones. Speed had won the tonnage war. Winter sea temperatures would soon dictate new terms. Richmond, California, 1942. Inside a darkened training classroom at Kaiser Yard No. 1, instructional reels demonstrated the fundamentals of shielded metal arc welding to new hires recruited from farms, railroads, and retail shops across the West. The films, produced by the United States Office of Education, showed proper electrode angle, travel speed, and arc length for various joint configurations. After watching films, trainees practiced on steel coupons under the supervision of lead welders, learning to strike an arc, maintain a consistent bead, and recognize common defects such as undercut, overlap, and porosity. Qualified welders then graduated to actual deck seams on hulls under construction. The process demanded concentration and a steady hand, but not the years of apprenticeship required for riveting. A motivated trainee could qualify for production welding in 4 to 6 weeks. Women comprised a substantial fraction of the welding workforce. One publicity photograph from Richmond Yard No. 2, dated 14 May 1943, shows a welder identified only as J. Howard, completing a vertical seam on a transverse bulkhead. She wears a leather jacket, protective goggles, and a welding hood decorated with the yard's insignia. The caption notes she had been a department store clerk 6 months earlier. Another photograph from the same period shows a team of 5 women welders working on a double-bottom section. Their names listed as Betty Reed, Margaret Elkins, Vera Foster, Ruth Simons, and Lucille Davis. These images, widely reproduced in newspapers and magazines, symbolized industrial mobilization but understated the physical demands and hazards of the work. Welding in confined spaces with poor ventilation exposed workers to metal fumes that caused respiratory irritation. Flash burns from ultraviolet radiation damaged unprotected skin. Sparks ignited clothing and started fires in areas containing flammable materials. Yards maintained first aid stations and kept ambulances on standby, but injuries were common and occasionally fatal. Designers optimized the EC2-SC1 hull for assembly speed and flat plate geometry to facilitate prefabrication. Standard dimensions measured 441 feet length overall, 57 feet beam, and 37 feet depth to the main deck. Displacement at loaded draft approximated 14,500 tons. A triple expansion reciprocating steam engine delivered 2,500 indicated horsepower for a service speed of 11 knots. With fuel capacity sufficient for approximately 17,000 nautical miles at economical speed. The machinery occupied a midship engine room. Holds fore and aft provided 10,441 gross registered tons of cargo capacity. 5 cargo holds were served by masts and booms capable of handling individual lifts up to 30 tons. Steel plate thicknesses ranged from 3/8 inch for decks and inner bottoms to 3/4 inch for shell plating at the load waterline. Framing consisted of transverse bulkheads at approximately 60-foot intervals, longitudinal stringers along the turn of bilge, and deck girders supporting hatch openings. Welded joints replaced traditional lapped, riveted seams, creating continuous load paths through the hull girder. Engineers understood that this continuity improved watertight integrity compared to riveted construction, where seepage through rivet holes was accepted as normal. Riveted ships could leak but remain afloat. A crack could not propagate beyond a single strake, because each rivet represented a mechanical discontinuity that arrested crack growth. Every rivet hole introduced a stress concentration, but the overall effect was beneficial because the discontinuous nature of the joints prevented catastrophic propagation. Welded hulls eliminated leakage and reduced weight, but they also removed the natural crack arrest features of riveted construction. A crack initiating in a welded hull encountered no impediment to growth until it reached a deliberate structural discontinuity such as a bulkhead or a change in plate thickness. Coast Guard circulars from mid-1942 noted occasional tearing at deck openings in field reports. These incidents were logged as non-critical and attributed to minor fabrication irregularities or isolated material defects. Inspectors drilled arrest holes at crack tips and recommended monitoring during subsequent voyages. The cracks typically measured 10 to 15 feet in length and appeared to stabilize after drilling. Ultimate tensile strength of the specified steel met or exceeded 30,000 pounds per square inch at room temperature. Yield strength exceeded 17,000 pounds per square inch. These values satisfied classification society rules and Navy specifications. Low-temperature toughness had not yet emerged as a design driver. Few West Coast laboratories possessed the equipment to measure notch impact energy at sub-zero temperatures, and no specification required such testing. The prevailing belief held that a material strong enough to support design loads would not fail in service. The North Atlantic was about to conduct an experiment at full scale that would overturn this assumption. North Atlantic. Winter 1942 to 1943. Convoy commodores received night orders as sea state climbed and ice accumulated on railings, lifeboats, and gun tubs. Typical winter convoys comprised 30 to 60 merchant vessels escorted by destroyers, corvettes, and occasionally an escort carrier. Formation steaming required precise station keeping despite darkness, poor visibility, and heavy seas. Radio silence prevented communication except by signal lamp or flag hoist. Lookouts scanned for periscopes, torpedo wakes, and floating mines. Gunnery crews remained at action stations throughout daylight hours when Luftwaffe bombers posed the greatest threat. At night, the primary danger shifted to U-boats stalking on the surface, using diesel engines to achieve speeds exceeding 15 knots, fast enough to outrun most escorts and position ahead of the convoy for submerged attack at dawn. Merchant captains aboard vessels like SS Patrick Henry and SS William Clark filed after-action reports praising the welded hulls as tight, dry, and strong Patrick Henry. The first Liberty ship entered service in December 1941, and completed multiple Atlantic crossings without structural incident. William Clark followed in March 1942. Both vessels survived the war and remained in commercial service through the 1950s. United States Shipping Board statistical compilations indicated a structural defect incidence below 1% across the Liberty fleet through December 1942. Public statements from the Maritime Commission framed the program as the bridge to victory. Press releases highlighted production milestones. 500 ships by September 1942, 1,000 by April 1943. Photographs of launches, often featuring prominent sponsors such as Eleanor Roosevelt or Hollywood actresses, dominated newspaper coverage. The narrative emphasized industrial might and inevitable Allied victory. Privately, however, inspectors logged approximately 45 cases of plate tearing near deck openings during this same period. Most cracks measured between 10 and 40 feet in length and appeared to initiate at square hatch corners or at the intersection of longitudinal seams and transverse bulkheads. Typical inspection reports included sketches showing crack location, measurements of crack length and width, and notes on apparent initiation points. Recommended remediation consisted of drilling arrest holes at crack tips, typically 3/4 inch diameter, and installing external doubler plates or internal stiffeners to redistribute stress. The working assumption held that small cracks, once arrested, posed no threat to vessel safety. This assumption rested on extensive experience with riveted hulls, which routinely sustained localized damage without catastrophic consequence. Cracks in riveted ships arrested naturally at rivet lines. Reinforcement and routine monitoring sufficed to ensure continued operation. The behavior of welded hulls under similar conditions remained untested on a large scale. Sea surface temperatures on the northern convoy routes frequently dropped below -10 degrees Celsius during January and February. Air temperatures could reach -20 degrees Celsius or lower when Arctic air masses moved south. Under these conditions, thermal gradients developed between ballast tanks warmed by residual engine room heat and shell plating exposed to Arctic wind and spray. The temperature difference could exceed 30 degrees Celsius across a thickness of only inches. Steel contracts when cooled, inducing tensile stress. When combined with residual welding stress and operational loads from wave action, total stress could approach or exceed the material's yield strength. When cracks occurred, they typically aligned longitudinally along shear strakes or upper deck seams where tensile stress is concentrated during sagging conditions, when wave crests supported the bow and stern while the midship section sagged into a trough. Notation sheets from Lloyd's Register surveyors and United States Navy Board of Inspection officers marked these cases with terms like monitor and non-critical. The documents reveal a pattern of incremental recognition rather than sudden alarm. A report dated 6 February 1943 from Liverpool notes, crack 22 feet long at starboard shear strake forward of number 2 hatch. Arrested by drilling, recommend monitoring. A similar report from Reykjavik dated 18 February describes multiple short cracks at hatch corners. Longest 14 feet, drilled and reinforced, vessel cleared for service. Neither report suggests systemic failure or recommends grounding the vessel. Operational confidence remained high through the winter of 1943. Losses to U-boat torpedoes commanded far more attention than structural failures. Convoy HX-229 lost 13 ships to submarines in March 1943. None of the losses resulted from structural failure, but the tactical situation dominated post-voyage analysis. Nevertheless, within 12 months, one crack initially categorized as non-critical would run the entire length of a ship in seconds, demonstrating a failure mode that traditional maritime engineering had never encountered. Portland, Oregon. 22 January 1943. The Schenectady had been moved to an outfitting berth after launching on 15 December 1942. The launch ceremony had proceeded without incident. A local dignitary christened the vessel with champagne, and the hull slid down the ways into the Willamette River to polite applause from invited guests and yard workers. During the subsequent weeks, workers installed cargo booms, completed accommodation spaces, loaded spare parts and consumable stores, and conducted sea trials of machinery systems. Weather conditions on the morning of 22 January were calm. Dockside records show light winds from the northwest at 5 to 7 miles per hour, clear skies, and an air temperature of 4 degrees Celsius. Overnight low temperatures had reached -1 degree Celsius. No vessel movement was scheduled. The ship floated at rest alongside the pier with minimal load aboard, approximately 1,000 tons of stores and equipment, and no stress beyond the static weight of the hull and fittings. Ballast tanks contained approximately 3,000 tons of water distributed to maintain proper trim. Draft forward measured 14 feet. Draft aft measured 16 feet. These values indicated proper longitudinal balance for a vessel in the outfitting stage. At 10:15 hours, dock personnel heard a sharp report described by several witnesses as similar to a rifle shot, followed immediately by a series of secondary sounds characterized as tearing or ripping. Longshoremen loading crated truck parts into number 3 hold reported feeling the deck shudder beneath their feet. The ship's master, who was in the chart room reviewing loading documents, ran to the bridge wing and observed the deck separated by a visible gap amidships. Within 2 to 3 seconds, the Schenectady sagged visibly at the bow and stern as the midship section lost structural continuity. A fracture had opened across the entire deck at approximately frame 53, roughly at the midpoint of the cargo hold region, propagated downward through the shell plating on both sides, and extended across the bottom plating. The vessel remained afloat but effectively broken into two halves connected only by the keel bar and lower longitudinal structure. Yard security personnel evacuated workers from the vessel within minutes. Fire crews stood by with hoses charged, fearing that the fracture might have ruptured fuel oil tanks or severed electrical cables, but no fire developed. Pumps were rigged to maintain bilge levels while engineers assessed stability. The separated hull sections settled differentially, with the bow rising slightly and the stern sinking until it grounded on the river bottom. Photographers arrived within the hour and documented the failure. Images show the deck separated by a gap measuring several inches, with fractured edges exhibiting a crystalline, faceted appearance rather than the fibrous tearing characteristic of ductile overload. The fracture surfaces appeared bright and reflective, resembling broken cast iron more than structural steel. This visual distinction became one of the defining characteristics used to identify brittle fracture in subsequent investigations. Yard investigators and naval architects inspected the fracture surfaces and collected samples for metallurgical examination. Howard I. Chapin, a civilian naval architect employed by the Maritime Commission, participated in the initial survey. His report, filed on 27 January, noted that the fracture surface shows a crystalline appearance with cleavage facets and chevron patterns pointing toward the initiation site. Chapin later summarized the finding in testimony before a commission investigating board. The steel failed not in strength, but in nature. Mechanical tests on plate samples removed from the fracture zone confirmed that tensile strength and yield strength met specification requirements. Tensile strength measured 32,000 pounds per square inch. Yield strength measured 19,000 pounds per square inch. Both values exceeded minimum requirements. Chemical analysis showed carbon content of 0.21%, manganese 1.02%, and sulfur 0.035%, all within specification limits. The failure had not resulted from overload or from steel that was too weak in the conventional sense. Instead, the material had transitioned from ductile to brittle behavior at a temperature well above the freezing point of water. Fracture surfaces revealed cleavage facets, flat, reflective planes aligned with crystal lattice orientations, indicating that the crack had propagated by separating atomic planes rather than by the energy-absorbing process of plastic deformation and void coalescence that characterizes ductile fracture. Subsequent analysis traced initiation to stress concentrations near structural discontinuities, specifically at the intersection of deck plating and a transverse bulkhead where residual welding stresses had not been relieved. Metallographic examination of sections through the weld revealed a coarse-grained heat-affected zone with evidence of hydrogen cracking, a form of delayed cracking that can develop hours or days after welding if proper preheat is not maintained. Residual tensile stress in the vicinity of a weld can approach or exceed the yield strength of the parent material. When added to service loads, even minor external stresses can drive a crack. At low temperature, the steel's resistance to crack propagation, its fracture toughness, had collapsed. The welded hull, lacking the crack arrest features inherent in riveted construction, allowed unimpeded propagation once initiation occurred. A flaw that might have been benign in a riveted ship, where it would have arrested at the first rivet line, became catastrophic in a continuous welded structure. The Schenectady Incident Report, filed with the Maritime Commission on 27 January, included fracture photographs, dimensional sketches, metallographic images, and a listing of plate heat numbers for traceability to the steel mill. Recommendations called for increased inspection of similar vessels, investigation into material specifications and welding procedures, and consideration of design modifications to provide crack arrest features. The report did not use the term brittle fracture. The vocabulary had not yet entered common usage among shipbuilders, but the phenomenon was now undeniable. A sound hull, at rest in calm conditions, had split in two without external impact or overload. Similar failures would be logged within months, not in protected harbors but under convoy conditions in the open ocean, where the consequences could be far more severe. Greenland Run, February through April 1943. Convoys bound for Reykjavik and Murmansk encountered conditions more severe than those in Portland. Air temperatures on the Denmark Strait route routinely fell to -20°C. Spray froze on contact with steel, building layers of ice that added top weight and reduced stability. Deck crews chipped ice from lifeboats, ventilators, and gun positions. During routine inspections, bosuns on several vessels discovered cracks in deck plating that had not been present at the previous examination. Some measured 15 to 40 feet in length, running longitudinally along the shear strake or adjacent to hatch combings. Temporary repairs consisted of drilling half-inch holes at crack tips to relieve stress concentrations, then welding stiffeners or external doubler plates over the affected area. Emergency welding in sub-zero temperatures required portable shelters and preheat to prevent hydrogen cracking in the repair welds themselves. Convoy commodores filed incident reports upon arrival in port. British Lloyd's Register surveyors and United States Navy Board of Inspection officers consolidated these reports and forwarded summaries to the Maritime Commission and Bureau of Ships. By May 1943, documentation existed for approximately 60 notable cases of cracking in Liberty ships operating on northern routes. Statistical analysis suggested that roughly one vessel in 30 exhibited significant structural damage attributable to low-temperature embrittlement rather than battle damage, collision, or heavy weather. Riveted Empire-type vessels, British-built cargo ships of similar size and mission, showed no catastrophic splits. The distinction between riveted and welded construction could not be ignored. Survey sheets from this period contain annotations such as propagating longitudinal crack at shear strake frame 82, and recommendations to install rounded cutouts at hatch corners and drill arrest holes at crack termini. These measures addressed symptoms but did not resolve the underlying cause. The problem lay in the intersection of material behavior, structural geometry, and operating environment. Semi-killed carbon steels commonly used in shipplate contained sulfur and phosphorus levels that promoted segregation of brittle phases at grain boundaries. Square hatch corners acted as geometric stress risers, locally amplifying applied stresses by factors of 2 or 3. Residual stresses from welding remained locked in the structure unless relieved by post-weld heat treatment, a procedure rarely applied to large ship structures. Cold exposure triggered the ductile to brittle transition, reducing the material's ability to absorb energy and resist crack propagation. Riveted designs inherently provided crack arrest at each lap joint. The discontinuity between adjacent plates, connected by discrete mechanical fasteners, prevented a crack from propagating beyond a single strake. A riveted ship could sustain extensive local damage and remain seaworthy. Welded construction eliminated these natural arrest points, creating a continuous load path with no impediment to crack growth once initiation occurred. This fundamental difference had not been fully appreciated during the design phase, when attention focused on strength, watertightness, and speed of construction. Fracture mechanics as a formal engineering discipline did not exist in 1943. The concepts and test methods required to quantify fracture toughness and predict crack behavior were still under development. Laboratories in Britain and the United States now began receiving samples of broken plate, and a new vocabulary began to take shape. Cambridge University. July 1943. Dr. Constance T. Tipper received her first shipment of fractured Liberty ship plate under a Ministry of Supply contract to investigate structural failures in welded vessels. Tipper, a petrologist by training, had developed expertise in crystallography and fracture analysis during earlier work on coal mine roof falls. She adapted these techniques to steel, preparing polished sections and examining fracture surfaces under optical microscopy. Her laboratory possessed one of the few impact testing machines in Britain capable of sub-zero operation. By chilling specimens in a mixture of dry ice and alcohol, she could simulate North Atlantic temperatures and measure the energy absorbed during fracture. Test results demonstrated a sharp transition in fracture appearance and energy absorption as temperature decreased. At 20 degrees Celsius, specimens fractured with extensive plastic deformation, exhibiting a fibrous, gray surface and absorbing substantial energy before failure. At minus 20 degrees Celsius, the same steel broke with minimal deformation, showing a bright, crystalline faceted surface and absorbing less than 1/5 the energy. The transition temperature, the point at which behavior shifted from ductile to brittle, varied with composition and processing history but typically occurred between 0 and minus 30 degrees Celsius for the steels used in Liberty ship construction. This temperature range overlapped precisely with the operating environment of North Atlantic convoys. Tipper's analysis revealed that semi-killed steels with higher sulfur content exhibited greater notch sensitivity and a higher ductile to brittle transition temperature. Killed steel, deoxidized with aluminum or silicon, showed improved toughness. Grain size also influenced behavior. Finer grains produced by controlled rolling yielded tougher material than coarse grains resulting from excessive hot working temperature or slow cooling. These metallurgical variables had received little attention during the rush to production. Specifications emphasized tensile strength and weldability. Toughness at low temperature was not a specified property, and few suppliers routinely measured it. Tipper's 1944 report, titled Investigation of the Fracture of Welded Ships, correlated low-temperature toughness with composition, processing, and microstructure. She noted that square hatch corners significantly raised stress intensity at the corner radius, creating a crack-driving force that could exceed the material's resistance even under moderate applied loads. Her work provided the scientific foundation for design changes already being implemented empirically in shipyards. Consolidated wartime statistics, compiled from United States and British sources, eventually identified approximately 1,200 vessels with documented cracking and at least 19 ships that broke completely in two. The majority of catastrophic failures occurred in Liberty ships, T2 tankers, and other all-welded designs operating in cold water. Establishing the concept of a ductile to brittle transition temperature reframed the problem from a question of welding technique alone to a broader issue of material behavior, structural geometry, and operating environment. Engineers now understood that strength and toughness were distinct properties. A steel could be strong, capable of supporting high loads without yielding, yet brittle, failing suddenly with little energy absorption once a crack initiated. Conversely, a slightly weaker steel with superior toughness might prove more reliable in service because it resisted crack initiation and arrested propagating cracks before they became catastrophic. This insight drove changes in material specifications, fabrication procedures, and design practices. Production, however, could not stop. The Maritime Commission needed to apply fixes without halting output. Washington, D.C. August 1943. The Maritime Commission issued Directive M27, instructing shipyards to proceed with construction while incorporating temporary mitigation measures fleet-wide. A pause in production would jeopardize the tonnage war and potentially delay the planned invasion of Europe. Allied shipping losses to U-boats had declined following the introduction of escort carriers, improved sonar, and long-range patrol aircraft, but replacement tonnage remained critical. The Commission directed yards to implement modifications in place, retrofitting vessels already in service and incorporating changes into new hulls on the building ways. Specific measures included drilling crack arrest holes at the corners of existing cracks to prevent further propagation, rounding hatch corners to reduce stress concentration, and installing doubler plates and external straps at critical seams. Yards added riveted crack arrestor straps at intervals along longitudinal seams, creating mechanical discontinuities similar to those present in riveted hulls. Some facilities introduced local stress relief heat treatment for highly stressed regions, although full post-weld heat treatment of an entire hull remained impractical. Welding procedure specifications were revised to require preheat for thick sections and to control interpass temperature to reduce residual stress and avoid hydrogen cracking. The aggregate weight penalty for these modifications approached 10 tons per ship, slightly reducing cargo capacity but significantly improving resistance to fracture. By the end of 1943, approximately 1,500 Liberty ships had incorporated the changes. Statistical tracking indicated that crack incidents on cold route operations decreased by roughly 30% among modified vessels compared to unmodified sisters operating in similar conditions. The modifications addressed geometric stress risers and provided basic crack arrest features, buying time until material specifications could be improved. Geometry control and mechanical crack arresters interrupted propagation, but the steel itself, the base material and weld metal, still required a wartime solution. Maritime Commission engineers worked with Bureau of Ships reviewers and Lloyd's surveyors to disseminate best practices. Field circulars included detailed sketches showing radius transitions at hatch corners, recommended stop drill patterns for crack arrest, and guidance on doubler plate installation. These documents reached shipyards, repair facilities, and vessel operators worldwide. The empirical knowledge gained from thousands of vessels in service provided a data set unprecedented in maritime engineering. Failures, though costly in material and occasionally in lives, advanced understanding of structural integrity in ways that peacetime development could not match. Symptoms were being managed. The underlying cause, the material's response to low temperature, still awaited a comprehensive metallurgical answer. Bethlehem Steel Works and United States Naval Research Laboratory. 1944. A plate coupon emerged from a dry ice bath at -40 degrees Celsius and was mounted in a tensile testing machine equipped with a high-speed camera. Engineers applied a notch to simulate a crack tip, then loaded the specimen. In a fraction of a second, a crack raced across the plate at nearly 1,000 meters per second, the entire event captured on film. Slow-motion replay showed the crack tip advancing ahead of any visible deformation, cleaving the steel with minimal energy absorption. This behavior stood in stark contrast to room temperature tests, where cracks propagated slowly if at all, surrounded by extensive plastic zones that absorbed energy and resisted propagation. Earlier design philosophy had equated strength with safety. If a material could support design loads without yielding, it was deemed adequate. Experiments now showed that fracture toughness, the material's resistance to crack initiation and propagation, was the controlling metric in cold service. A material could be strong yet susceptible to catastrophic fracture if it lacked sufficient toughness at the operating temperature. This realization shifted metallurgical research toward understanding and quantifying toughness. George R. Irwin, a physicist at the Naval Research Laboratory, developed mathematical frameworks for describing the stress field near a crack tip and introduced the concept of a stress intensity factor, later designated K. Irwin's work laid the foundation for linear elastic fracture mechanics, a discipline that would transform structural design across aerospace, civil, and mechanical engineering in the post-war decades. Navy and industry metallurgists refined procurement specifications to favor steel compositions with improved low-temperature toughness. Revised standards called for lower carbon content, typically around 0.15%, with controlled manganese and silicon additions and strict limits on phosphorus and sulfur. Aluminum-killed steels replaced semi-killed grades. Controlled rolling practices produced finer grain structures. These changes increased toughness without sacrificing strength or weldability. Ultrasonic testing entered quality control procedures, allowing detection of internal flaws that visual inspection and radiography might miss. Welding procedures codified preheat and interpass temperature control for heavy welds, reducing residual stress and avoiding cold cracking. The aggregate effect of these improvements began closing the failure envelope. Vessels constructed after mid-1944 using upgraded steel and procedures showed markedly reduced crack incidence even on the most demanding routes. Charpy V-notch impact testing, developed in Europe before the war but not widely adopted in the United States, became a standard acceptance criterion. Specifications required minimum impact energy at a specified test temperature, ensuring that materials retained adequate toughness in service. By 1945, the Liberty ship program had produced more than 2,700 vessels. Early hulls required extensive monitoring and modification. Late production units incorporating metallurgical and design improvements proved far more reliable. The lessons learned extended well beyond shipbuilding, influencing standards for pressure vessels, pipelines, bridges, and offshore structures in the decades that followed. Early internal notes from the Naval Research Laboratory began using terms like stress intensity and fracture toughness that would later be formalized in engineering codes and textbooks. The operational concept now designated as K, representing the magnitude of the stress field at a crack tip, emerged from this wartime work. Tougher steels combined with inspection protocols and rigorous procedure control began to close the failure envelope. The fleet needed proof, however, at full scale and under ship-level stresses. That validation would come from vessels that survived the war and continued in service through the 1950s and 60s, accumulating operational data that confirmed the effectiveness of the wartime fixes. North Atlantic and Pacific. 1945 through 1946. Modified Liberty ships returned to service with rounded hatch corners, riveted crack arresters, and improved steel specifications. Operators monitored performance across a range of service conditions. Vessels operating on cold water routes, Mormont's convoys, Alaska supply runs, and Trans-Pacific winter crossings provided the most stringent test environment. Statistical tracking indicated that catastrophic fractures became rare among ships incorporating the full suite of metallurgical and design improvements. Cracks still occasionally appeared, but they arrested at design discontinuities rather than propagating the length of the hull. Drilled holes at crack tips proved effective in preventing further extension. Doubler plates and external straps reinforced high-stress zones. The combination of geometry control, mechanical crack arresters, and tougher base material provided defense in depth against brittle fracture. Ships that survived the war entered commercial service. Many remained in operation for more than 20 years, carrying grain, ore, and manufactured goods on global trade routes. Their service records validated the wartime modifications. Vessels built in 1942 and 1943, before the problem was fully understood, required ongoing inspection and periodic repair. Units delivered in late 1944 and 1945, incorporating improved material and design from the outset, proved remarkably durable. Insurance underwriters adjusted premium rates based on construction date and modification status, creating economic incentives for operators to retrofit older vessels with crack arrest features. Post-war analysis by the United States Coast Guard and the American Bureau of Shipping identified approximately 240 Liberty ships that sustained significant structural damage during their service lives. Of these, fewer than 20 broke completely in two. The majority of catastrophic failures occurred between 1943 and mid-1944, before systematic fixes were applied. After 1944, as metallurgical improvements and design changes took effect, the failure rate declined sharply. This real-world validation confirmed that brittle fracture could be controlled through a combination of material selection, structural design, fabrication quality, and inspection. The Liberty ship experience demonstrated that even a well-intentioned and urgent wartime program could encounter unexpected failure modes when pushing the boundaries of established practice. The shift from riveting to welding achieved dramatic improvements in production speed and hull integrity, but it also eliminated traditional crack arrest mechanisms without initially recognizing the consequences. The solution required contributions from shipbuilders, steel producers, metallurgists, and naval architects working under intense time pressure. The knowledge gained, formalized in design codes, material specifications, and inspection procedures, shaped engineering practice for the remainder of the 20th century and continues to influence safety standards today. The brittle fracture crisis of the Liberty ships established fracture mechanics as an essential engineering discipline. George R. Irwin's stress intensity factor, initially developed to explain ship failures, became the cornerstone of modern fracture analysis. Engineers designing pressure vessels, pipelines, aircraft structures, and offshore platforms now routinely calculate stress intensity factors and compare them to material fracture toughness to assess structural safety. The American Society for Testing and Materials developed standardized test methods for measuring fracture toughness, including the K1C test for plane strain fracture toughness and the Charpy V-notch impact test for screening materials. These tests ensure that materials possess adequate resistance to crack propagation under service conditions. Design codes for bridges, pressure vessels, and other critical structures now mandate fracture critical member inspections and require materials with specified minimum toughness at the lowest anticipated service temperature. The concept of design against fracture complements traditional design against yielding, recognizing that strength alone does not guarantee structural integrity. Weld quality requirements emphasize full penetration, proper fusion, and freedom from crack-like defects. Non-destructive examination techniques, ultrasonic testing, radiography, magnetic particle inspection, detect flaws before they reach critical size. Fitness for service assessments evaluate whether a detected flaw is safe to leave in place or requires repair, using fracture mechanics calculations to predict remaining service life. The Liberty Ship program also influenced welding education and certification. The American Welding Society developed standardized training curricula and qualification tests for welders and welding inspectors. Procedure qualification records document welding parameters, joint geometry, and acceptance criteria for each specific application. Welder performance qualification ensures that individual welders can produce sound welds meeting code requirements. These practices, now routine across shipbuilding, construction, and manufacturing, trace their origins to lessons learned during the Second World War. material specifications evolved to include toughness requirements alongside traditional strength properties. Steelmakers developed controlled rolled, normalized, and quenched and tempered grades offering superior low-temperature toughness without excessive cost. Offshore oil platforms operating in the North Sea, Arctic pipelines transporting natural gas, and cryogenic storage tanks for liquefied gases all benefit from metallurgical advances driven by the Liberty ship failures. The engineering community learned that failure analysis, properly conducted and disseminated, prevents future disasters. The wartime collaboration between industry, academia, and government established a model for addressing complex technical challenges that continues to inform engineering practice. By 1970, most surviving Liberty ships had been scrapped or converted to stationary storage. A few remained in commercial service into the 1980s, testimony to their robust basic design and the effectiveness of mid-war modifications. Two vessels, SS Jeremiah O'Brien and SS John W. Brown, were preserved as museum ships. Visitors can board these vessels, walk their decks, and examine the welded seams that once sparked a metallurgical crisis and a scientific revolution. The squared hatch corners visible on early photographs have been replaced by rounded contours. Riveted crack arresters, installed during wartime service, still mark the shear strakes. These details, invisible to most observers, represent hard-won knowledge purchased at the cost of material losses and, in some cases, lives. The Liberty ship story illustrates the interplay between urgency, innovation, and unintended consequences. The decision to adopt all-welded construction achieved dramatic gains in production speed and made possible the massive sea lift that sustained Allied operations in Europe and the Pacific. The brittle fracture problem, unforeseen at the program's outset, demanded rapid investigation and solution under wartime pressure. The response, drawing on metallurgy, material science, structural engineering, and practical shipyard experience, laid foundations for modern fracture mechanics and transformed engineering practice across multiple industries. This legacy persists in design codes, material specifications, inspection procedures, and the education of engineers who work with structures subjected to demanding service conditions. The men and women who built these ships, welders, riveters, fitters, inspectors, engineers, deserve recognition not only for their output but for their adaptability. They learned new skills, accepted demanding work schedules, and responded to technical challenges with pragmatic solutions. The scientists and engineers who investigated the failures, Constance Tipper, George Irwin, and dozens of less-remembered colleagues, advanced human understanding of materials under stress. Their work continues to protect lives and infrastructure today. Engineering progress emerges not only from success but from failure rigorously examined. The Liberty ship fractures forced a confrontation with phenomena that existing theory could not explain and prompted development of new analytical tools. The resulting discipline of fracture mechanics serves engineers worldwide, preventing catastrophic failures in structures ranging from aircraft to power plants to oil rigs. The lesson extends beyond technical details. Urgent circumstances may demand innovation, but innovation without thorough understanding carries risks. When those risks materialize, the appropriate response combines immediate mitigation with systematic investigation to prevent recurrence. 2,710 Liberty ships entered service between 1941 and 1945. They carried 10 million tons of cargo, delivered 15 million tons of supplies to Allied forces, and transported millions of troops and refugees. Their contribution to victory was indisputable. That a fraction fractured under specific conditions does not diminish the program's achievement. Instead, the fractures provoked advances in material science and engineering that improved safety across every field touched by welded steel construction. The Liberty ships served their immediate purpose and, through the failures of a few, bestowed a lasting gift of knowledge. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive.